Bayes classifier is a collection of classification algorithm. So it is actually helps you to like predict your categorical variables. Okay, so it belongs to family of simple probabilistic classifiers, which is like based on applying Bayes theorem. Okay, so which has an like a strong assumption between features that they are like independent of each other. So here we'll be like only able to like predict only the categorical variables, but you can also like able to compute variables with both continuous and categorical data. Okay, so this has been like used in a lot of areas like credit approval, like whether a person or a company can be like provided loan or not. So in marketing, to target the right person for advertising, it has been used, and in medical diagnosis, like whether the person has a certain disease or not. This database has been used, and it's been used in various other places like to filter spam messages from your email, and in text classification, and also in a lot of other areas has been used. Okay, this one is a very simple algorithm, but it is has a very big effect on the data. When you have very a small amount of training data, database works wonder. Okay, so like all the other algorithms, this also has two-step process where you have to like form a model. You have to create a model, and then after that you have to like apply the training data set so that you can able to like predict your future objects or unknown objects. So you'll be like using accuracy, specificity, and like other things to like find out whether the model is like performing better or not. Okay, so we always have to use a separate test set from your validation and training set, so that you'll be able to have a very good model. Otherwise, you'll be like very overfitting model. Okay, all this basic assumptions remains the same. Okay, yeah. So let's get into this Bayesian classification. So as I told you, it's one of a very basic statistical method for classification, which is based on probability methods. So this is like proposed by Thomas Bayes. So that's why it is called as Bayes theorem. As I told you before, you can able to like solve problems which has both categorical and continuous data. Okay, so the formula for Bayes theorem is like probability of occurrence of event C given X equal to probability of X given C multiplied by probability of C divided by probability of X. So here we have a event C given X, which is actually called as a posterior probability. So I believe you already know what is posterior probability and prior probability. If you have clarifications on that, I have few notes added in this document, which I'll be like sharing to you later, so that you can able to understand this better as well. Okay, so prior probability is the actual probability, the original one, which before you are introducing a new evidence. Okay, so P of X is your prior probability of for a predictor, whereas P of C is also a prior probability. This is just a usual probability that always you have before you introduce an evidence. So here we have an evidence of X, occurrence of event C given X. Okay, so that maybe you can just say during winter, maybe X is an event of snowing, and C is a people consuming hot beverages. Okay, so how many people trying to consume hot beverage when it is snowing? So maybe that you can call it as a posterior probability. Okay, so when you have many different class labels, so for the event X, So we can just like, calculate the likelihood based on the formula. Probability of C of X is equal to probability of the event X1 given C until probability of the event Xn given C multiplied by probability of C. Okay. So I believe this is actually based on conditional probability formulas. I believe if you have understood that, you'll be able to understand this. Please refer to my previous notes so that you can able to understand this. So P probability of C given X is a posterior probability which you're like trying to predict, and probability of C is a prior probability of a class, whereas X is a prior probability of a predictor here, and then probability of occurrence of event X given C is a likelihood. Okay. So we'll be able to like apply this formula in a given example so that you'll be able to understand better. So for example, we are trying to predict whether the person is going to buy a computer or not if he is 35 years old and he earns $40,000 as an annual income and his credit rating is fat. Okay, so we are setting up a hypothesis saying that this customer will buy a computer. So let's see whether how we are going to able to apply this example and the formula together. So according to this, we have this occurrence of this hypothesis given X. Okay, so we have the prior probability of H, which is like the probability that the customer will buy a computer regardless of whether he's of certain age or have a good credit rating or income. I'm not looking to any of the other categories. So I'm just assuming whether the person will be able to buy a computer or not, which is your probability of P of X is the probability that the person that from a set of customers who's 35 years old and have a fair credit rating and earns 40,000, which is your real probability of X. Okay, so H of X is probability that the customer will be able to buy a computer if we know his age, credit rating, and income. Okay, this one. So probability of X over H. So here the customer is 35 years old and have a fair credit rating and earns 40,000, given that he has a bought computer. So he has bought the computer, but still we are trying to figure whether he's 35 years old, a good credit rating, and is earning 40,000. Okay, it's just a reverse of your posterior probability here. Okay, so posterior probability of H given X. So this is posterior probability of X given H. Okay, the condition is reversed. Okay, so now we are able to understand how the formula really works. So it'll be like looking into a very simple example so that you'll be able to understand this better. But before that, you have to understand a basic assumption based on Bayes operates. So this actually assumes that all the variables are like independent to each other. It assumes all the attributes are like completely independent, which is sometimes completely false, right? For example, a person who is like greater than 30 might have a chance of gaining more income than the person in his 20s, right? That's most of the time it is true. So but here Bayes doesn't believe that. It actually thinks it is completely independent of all these conditions, and that's why it's actually called as name based. Okay, so this model is like very name. Okay, so with that in mind, also we'll be like to a small example so that you'll be able to understand this better. So I'll be like having a small data set here which has information on what day it is. It's a weekday or a holiday or a weekend, and whether the store is providing discount or not, and whether the store is providing free delivery or not, and the customer has made a purchase or not. Okay, so it is a a small, simple shopping data set of a particular store. Okay, so whether the day is weekday, holiday, or a weekend, the discount is yes or no. No, free delivery is yes or no, purchase is yes or no. Okay, so we're trying to predict whether people are purchasing the product from the particular store given these three conditions. Okay, so first we have to create a frequency table based on the you know whether the customer is buying the product or not. Okay, so we got buying purchasing or buying is a dependent variable based on these three things are independent variables. So we're trying to create a frequency table with all the three independent variables along with the dependent variable. So we have buy and discount. So out of 30 people, 19 people have bought the product when there's a discount. One person has not bought, and sorry, five people have bought the product even that when there is no discount, and five people have not bought it when there is no discount. So likewise, during free delivery, when the shop is offering free delivery, 21 people have bought. When there is no free delivery, 2 people have bought. So when there is a free delivery, 2 people haven't bought. When there was no free delivery, 3 has bought. When there is no free delivery, 2 has not, 4 has not bought. Similarly, we have done that for a day as well. For weekday, weekend, and holiday. Okay. So now we'll be applying Bayes theorem on this example. So here we'll be having an independent variable by as an event A and all the rest of the variables as an event B. Okay, your discount, free delivery, and day, all these conditions will be event B. Okay, so here we'll be considering only day. Okay, so here I have a day frequency table, and then I am trying to compute a day likelihood table. Okay, so summation of all this, yes, for when the person has bought the product is 24, and when it is not the product, it is 6. So but on a weekday, I mean, out of 30 data we have, 11 where 11 purchases happened on a weekday, 8 on a weekend, and 11 on a holiday. Okay, so we are trying to compute the likelihood table for day and buy. So here it's 24, the summation is 24, likelihood for weekday and a person buying a product is 9 by 24. Here it is, summation is 6. So 2 by 6, 7 by 24, and here 1 by 6, 8 by 24, 3 by 6. Okay, for day, totally, here it is 11. For a weekday, the summation is 11. Okay, so for a week, it's 11 by 30, 8 over 30, 11 over 30. Okay, so now we are trying to find the probability of occurrence of event A, right? So for A, if the person has not bought the product, it is 6 over 30. 6 by 30, the number is 0.2. When it is a weekend, so we are trying to have an event of people buying on a weekday, which is event B. So we have on a weekday, it is 11 over 30, so 0.37. So P by A, which is trying to predict the week when there is a weekday and people have not bought. On a weekday, people have not bought is 2 by 6, 0.033, 0.33. Okay, you're just computing all the conditional probabilities here. Okay, so we have computed probability of event A and B given A. So for the probability of occurrence of event A given B, A is when the person is not buying on a weekday is equal to probability of person buying on a weekday and not buying on a weekday multiplied by probability of person not buying divided by. it is a weekday. So we're just like substituting all these things that we have computed, and we get an answer 0.179. So almost 18%. Sorry. So this is a conditional probability of occurrence of event A, which is not buying on a weekday. So similarly, we are trying to assume the event A is buy. Earlier it was not buy. So here it is 24 by 30. Okay. So here it is 0.8. So here substituting that all is here, and then we are able to get an answer 0.817, and here it is 179. Okay. So that's how we computed the probability of a person buying a product on a weekday and the probability of a person buying not buying a product on a weekday. So here we are just had only one independent variable, whether what kind of day it is, right? So we have to include all the other events, like delivery and discount. Okay, so we had all this um, likelihood table computed from the frequency table for delivery and discount. Similarly we did for the day table. Okay, now we are going to assume that event A, whether the person is buying a product or not, and event B will be a day which is a holiday, when there is a discount, and when there is a free delivery. Okay, so now we are including combination of all the three factors in the occurrence of event B. Okay, so we are calculating conditional probability on all these conditions, whether the event B is equal to in a day is a holiday, discount is available, and free delivery is available, and the event A is not buying. So we are substituting that formula of when there is a probability of event A given B is equal to probability of when the person is not buying a product, and the discount is available, free delivery is available, and the day is a holiday. So we have to put this in the Bayes formula through Bayes theorem. So it's probability of the discount is equal to S when the person is not buying, multiplied by probability of occurrence of not buying when there's a free delivery, probability of not buying when the day is a holiday, multiplied by probability of not buying, whole divided by probability when there's a discount, when there's a free delivery, and when the day is a holiday. Okay, so you just have to look into this table and then substitute this here. So when there's a discount and when the person is not buying, you have to look into the likelihood table of discount. And there is when he is not buying, and this discount is 1 by 6. It's 1 by 6. In the free delivery table, we have to check whether the free delivery table is available, but the person is not buying. So 2 over 6 here. And here the days of holiday when the person is not buying. So it's 3 over 6 here. And totally when the person is not buying at all. Okay. So it's just 6 over 330. Whole divided by when there is a complete discount available, so it is 20 over 30. When there is a complete free delivery available is 23 over 30, and in the days of holiday, so 11 over 30. So when you compute this, you get an answer of 0.178. So we have calculated the occurrence of even if the person is not buying a computer when all three things are available. Okay. Similarly, we can compute the conditional probability on a purchase of a product when when your conditional evidence is like the day is a holiday, discount is S, free delivery is yes. Similarly, we have like expanded this formula and substituted this numbers from the likelihood tables, and then got a answer of 0.986 for the conditional probability when the person is like buying a product when it is a holiday and the discount and free delivery is available from the store. Okay, so you know so here the purchase is of probability for purchase is 0.986 and not purchase is 0.7, but it is just conditional probability, right? We just computed based on the Bayes theorem. We have to like convert these probabilities into likelihoods of occurrence of event. We have to like do some normalization event here. So for that you have to like compute a percentage for this. So the sum of probabilities is 1.164. Sum of both the probabilities is 1.164 because we have only two different class labels here, right? Whether the person is going to buy a product or not buy a product. Okay, so it's actually a binomial classification. So we just have like summing up only these two probabilities, 1.164, and then when you just divide each of the conditional probability, you'll be able to get a likelihood of purchase and likelihood of not purchase. So in percentage, you'll be able to find out. So almost 85% of the time, people will be able to like purchase. And for
Ma'am, I have
16%,
just a small doubt, ma'am. Shouldn't the sum of probabilities equal to 1, ma'am?
this is conditional.
Yeah, ma'am, but still they are complementary events, ma'am. A person can either buy or not buy. Given that it's the same situation that I have free delivery, I have a discount, and it's a holiday. So a person buying or not should be complementary, right, ma'am? So shouldn't their probabilities add to 1, ma'am? Because here it's going beyond 1. That's my doubt, ma'am.
See, you can add conditional probabilities, but this is not always equal to 1. Are you available? I could not hear you properly.
Ma'am, there seems to be some network issue. I did not hear what you said moments ago, ma'am.
Your
But
voice is
my
breaking, Tilak.
I chat, ma'am.
Okay. So please type in chat. So I'll finish that and get back to you. Okay, similarly, I have a different example. Okay, for another data that the person is like buying a computer based on the age, income, and whether he's a student or not, and on what is the credit rating. So the same example is like computed here. You will be like working on the probability of occurrence of event, a single event with only one dependent variable, and then with many dependent. Oh, sorry, one independent variable and many independent variables. Okay. So please, I don't have enough time to like explain all this. I'll be like sharing that. Okay. So where this name base has been used, as I told you, it's been used in a lot many areas apart from financial areas. It has been used in text classification and trying to check whether a message or an email is a spam or not. And it is being used in hybrid recommendation system as well. Okay, and then it has been used in a lot of you know online applications where when a person is like trying to predict the emotions or sentiments of a person. So it's been also used in the sentiment analysis. Okay. So the major advantage of naive Bayes is like it's very easy to implement. It's very simple. Once you just have enough knowledge on probability and conditional probability, you can just compute it. And then even if you have small amount of training data, you can able to like create a model and run over it. So, apart next to SVM, if you have small data, you can just use naive Bayes. So most of the time, you'll be able to get good accuracy. Whether the disadvantages is like it always have an assumption each of the classes like kind of independent of each other, as I told you earlier. And that's why it's called naive Bayes. And so sometimes because of that there might be a less of accuracy here. And so there will be like a lot of dependency among the other variables, which is like ignored. Okay. This is one of the greatest disadvantage for a naive Bayes. So we have like few challenges here. Okay, in naive Bayes, we'll just discuss about that right now. So this is one of the challenge, as I told you. This class conditional independence is one of the challenge here. Because of that, you will not be able to like give a good accuracy, but your calculations becomes very simple when compared to the rest of the algorithms. And the other one of the problem we have is a zero problem. Okay, so here we're trying to compute probability of occurrence of an event given a condition. Okay, if when you one of a particular event probability becomes zero, the whole event, I mean the whole conditional probability gets a zero for particular sample. Okay, and because of that we are not able to like get the right class labeling here. Okay, so it is like sometimes very expensive mistake that we might be like making. So to avoid that, we will be like we have to use a different method, which is called as Laplacian correction or Laplace estimator, which you'll be like uh, using the correction method where you will be like trying to like pretend that we have one more tuple in each of the you know values, so that you'll be able to like able to round up these decimals, or you'll be able to convert 0 to 1, so that your values become good, so that you'll be able to avoid a 0. Okay, so maybe I'll be able to like give you explanation with this example. For example, we have a person is buying a computer, and you have like 1,000 tuples for that. So we have income as a category. So we have zero values for, when the income is low. So we never had a value or even when the income is low. But we had 990 tuples for medium income and 10 tuples for high income. Okay. So usually the probability will be like 0.9 and 0.01, 0.99 and 0.01 for the events, right? But the other event becomes 0. So when you're like using this in the income value pair, you'll be able to like when you multiply the income with the rest of the probabilities in conditional probability, what will happen? The whole value becomes 0. So in order to avoid that, what do we do is like we just assume there is one tuple for the income and 991 tuples for the medium and 11 tuples for the high income. So your total summation becomes 1003. Earlier it was 1000 tuples. So adding one tuple for each of the category. So it becomes 1003. So 1 by 1003 becomes 0.001. And this values all everything changes. So you're correcting your probability estimate so that you are allowing a zero probability. Okay, hope you got this, but maybe I can just explain this here with the example. Imagine this. So imagine there was a zero value here. Okay, for a weekday, and the person is buying. So it was 24 over 30. Okay. So P of A is 0. And then if you're substituting this value, so it becomes 0 divided by 0.036, which becomes your 0. So your conditional probability cannot be 0, right? So to avoid that, you just adding double to each of the categories so that you'll be able to avoid this 0. Okay, so this method is called as Laplacian correction or Laplace estimator. So this is the sort of technical probability estimation. So in case if you have probability values of 0, so that you can conveniently avoid it. So most of them very training data, so it doesn't make me very big difference. Okay, hope you're able to understand this. So overall, is very simple and because you'll be able to understand easily and apply easily in very complex places as well, including text classification, email filtering, and analyzing the sentiments. It's been used in a lot of areas in ML and in NLP as well. Okay. So if you got any questions, maybe you can just ask right now.
Ma'am, I posted mine in the